Hi everyone. So let's see the assignment 9, that is our fusion special assignment. So let's start with the first question. You have to find the small signal voltage gain, and when you are finding the small signal voltage gain, you need to take lambda equals to 0, and then you have to find the small signal output resistance, and when you are determining the output resistance, you have to take lambda equals to 0.05 voltage inverse, and it is given that all the transistors are working in saturation region. So let's start with our first question. So you have to find the small signal voltage gain. So one thing I know is that certainly there will be GM term coming, right? If I need to find small signal voltage gain, there will be certainly a term of GM. And for finding the GM, you need to do the DC analysis. For finding the GM, I need to do the DC analysis because the GM value is not given. So first, let's just find the value of GM. Let's just do the DC analysis and then let's find the small signal voltage gain. Actually, when we used to find the small signal voltage gain, first we used to do the AC analysis. From there, I could get to know that I required the GM value, and then I would do the DC analysis. But since I have solved a lot of examples, since we are comfortable with the AC analysis now, so first we know that already we will be using GM value. So first we will find the value of GM. So let's start with the DC analysis. So let's do the DC analysis of the previous circuit that we have. Why we are doing the DC analysis? For finding the GM value. We don't need this R naught or anything in the DC analysis. Since you are doing the DC analysis, this capacitor will be gone. There is no use of this capacitor. This input will be shorted because that was the small signal input voltage, and this capacitor will be gone. So this complete part will be gone, right? Since this capacitor is open circuited, so this complete part will not come in action. Now let's take it here. So there will be something coming. There will be some DC voltage coming. That voltage would be 18 into R2 upon R1 plus R2, and that voltage is fed here. So basically, what I can do, I can remove this part. I can remove this part. And simply say that at this point 18 into R2 upon R1 plus R2 is fed. So at this potential 18 into R2 upon R1 plus R2 is fed. Your target is to find the GM value. All the transistors are matched. All are having the same mu and CXW by L VT value. All are having the same values. What is the current here? ID current is 200 microampere. Right? 200 microampere current would be flowing here. So what will be the value of GM? Why 200 microampere completely going here? Because there is no current going here. This was the gate terminal, no current going here, and no current would be coming here. So complete 200 microampere would be flowing through the MOSFET. What would be GM? GM would be root 2 into mu n CUX W by L ID. Mu n CUX value is 100 micro. So here we will get 200 micro Siemens. So this GM value, so from here, GM value you are getting is 200 micro Siemens. And what would be the value of 1 by GM by that? Can you calculate the value of 1 by GM as well? Because you would be needing, most probably you would be needing 1 by GM value as well. So if you calculate it, it would be 2 into 10 power 4, 5 kilo. This would be 5 kilo. So in the near future, there is high chance that we will be needing these two values. So here we did the DC analysis. Now we are going to do the AC analysis because we need to find the small signal voltage gain. First we are going to do the AC analysis now. So let's copy the same circuit that we have. So for AC analysis, what will happen? This capacitor will be shorted. This capacitor will be shorted. This capacitor is shorted. Now this 0 volt that is going, and it is shorting this node, right? This was shorted, so this 0 node is going and it is shorting this node. So let's just remove this one completely, and let's just short circuit this node. So this node is shorted, that I know. Well and good. There is no use of this. Where it was connected, it was connected like this. So basically there is no use of this now, right? Because this node is 0. In AC analysis, this node is 0 and this node is going here. So there is no use of this part now. This This part was just to make the potential divider to bias this circuit. So there is no use of this. Why this part was there? 18 R1 R2 to bias this circuit, with this potential. That's it. There is no use of this. Since this is shorted, there is no use of this part. So in the AC analysis, you can simply remove this part now. No use of this part. Since you are doing the AC analysis, current source will be open circuited. If current source is gone, then this much is left. This much is left. Right? And this capacitor will be shorted. This capacitor is shorted. Now, what this can be replaced with? From here to here, what do you see? 1 by Gm parallel with R0. I told you, right? From here to ground. From this node to ground, what do you see? 1 by Gm parallel with R0. R0 is not there, so this will be simply replaced with 1 by Gm. This will simply be replaced with 1 by Gm. That is equals to 5 kilo. So this configuration, this complete configuration can be replaced with 1 by Gm. So that will be 5 kilo. So this 195 kilo ohm will be in series with 5 kilo ohm. Are you getting this point? I will replace this complete configuration with 1 by 5 kilo, with 5 kilo. So this is how I will replace it. Because from here to ground I could see 5 kilo. So 5 kilo ohm will come in series with 195 kilo. But let's just not remove that. Let's just get the same circuit. In the next page we will make it completely. So this much of part is becoming 200 kilo ohm, right? This much of part is becoming 200 kilo ohm. This is very easy. It is not tough at all. You can do it on your own, right? That much of part, because even by seeing the circuit I could get to know this part will be gone. Now this will be gone, so it will be replaced with 1 by Gm, and this is V in. So 100 kilo ohm will be coming here, 200 kilo ohm will be here, and that will be fed to this MOS. Right? So this much you can do. The twist will come later on, because what you need to calculate V0 by V in. Take your notice towards V0. Take your notice towards V0. That is the most important thing. What is V0 here? Well and good. So yeah, so I can make the equivalent circuit on the next page now. What is my equivalent circuit? So in my equivalent circuit, what do I see? I have a 200 kilo ohm resistance, 200 kilo ohm resistance, which is grounded, right? 195 plus 5, and then with the 100 kilo ohm resistance, I have V in connected. Now whatever the voltage that I get, that will be fed to an amplifier, and this voltage will create some current, and that current will be flowing through the upper MOSFET as well. And gate node of this MOSFET is connected to ground. Drain is connected to a 60 kilo ohm resistance, and we have a supply VDD which will be grounded in the AC analysis. This will be grounded in the AC analysis, and here I am calculating my V0. This is my V0. So let's just call this node as Vx, this node as Vy. So what will be my V0? V0 will be Vx minus Vy. And this is very important, because you are going to mess up here. Let's see how many of you get the correct answer. So this seems like an easy problem now. This is a V in. So what is the node voltage coming here? It will be V in by 3, right? Because there is no current going here, so you can simply divide the potential. How will you divide the potential? It will be 2 V in by 3. I'm really sorry. How will you divide the potential? 200 kilo ohm divided by 200 plus 100 into V in. So this potential will be 2 V in by 3. So here you are getting 2 V in by 3. Since you are getting 2 V in by 3 here, so what will be the current? 2 Gm V in by 3. The current here, this is the potential 2 V in by 3. Current would be Gm into VGS. VGS value is 2 V in by 3. So 2 by 3 Gm V in. So now this same current will be flowing in the complete MOSFET, and same current will be flowing through the resistance. So the current here flowing is 2 by 3 Gm V in. So what do you think, what will be your V0? So if you write my V0 is 2 by 3 Gm into V in into 60K, and certainly there is a negative sign as well, right? Since it is flowing like this, so there will be a negative sign. So if you say this is your V0, then this is simply wrong. This is simply wrong. Why is it so? Because this is your Vx. V0 is the differential of Vx and Vy. So first you need to find this node, then you need to find this node, then you can say what will be your V naught? V naught will be Vx minus Vy, right? So whatever that you found here, that is Vx minus 2 by 3 Gm into V in. So basically this current into this resistance. So this is your Gm, right? So minus 2 by 3, what is the Gm value? Gm value was 200 micro, right? 200 micro into 60k into V in. So Vx potential is 12 minus 8 V in. So Vx potential I am getting is minus 8 V in. So this is the Vx potential. Now you need to find Vy. Try doing it on your own. Can you find Vy by your own? Find Vy. Your target is to find Vy now. So let's copy this circuit again. And now my target is to find Vy. This is my Vx. For now I can remove it because my target is to find Vy now. Let's just remove V naught as well. So everything is remaining same now. Now tell me, what do you see from here? What do you see from here? You see 1 by Gm resistance only. Say yes or no? Or forget about it. If this node is your Vy, then what is the current flowing upward? If this node is Vy, what is the current flowing upward? Gm Vy. Say yes or no? Because this is Vy, this node is Vy. So Vy minus 0 Gm into, sorry, Vy minus 0 into Gm. That would be the current. Gm Vgs is the current. Gm Vgs. I told you how to write the current. How to write the current. This potential minus this potential, then the current would be this. And this potential minus this potential, then the direction of the current would be this. So I am writing this potential minus this potential. So in the upward direction, Gm Vy current. Right? So here you can see that Gm Vy is equals to minus of 2 by 3 Gm V in, right? This current would be negative of this current. Gm Vy would be equals to minus 2 by 3 Gm into V in. So Vy would be equals to Gm would be cancelled, minus 2 by 3 V in. This is your Vy. So you have the value of Vx as well and Vy as well. Vx and Vy. So what will be your V naught now? V naught would be Vx minus Vy. Vx potential was minus 8 V in and Vy potential was 2 by 3 V in. Minus sign is there, that would be plus. So from here you are getting 2 by 3, 0.66. So minus 7.333. Minus 7.33 V in. What is the small signal voltage gain that you are getting? That is minus 7.33. That's it. This is the small signal voltage gain you are having. This was an amazing question, right? Because we are generally habitual of finding V naught like this. This is our habit. But the V naught was into two nodes. So we have to find the potential of two nodes, Vx as well and Vy as well. And based on that, you get the value of V naught, that is Vx minus Vy. From there, you would get to know the gain, that is minus 7.33. Well and good. Now the other task is to find the R naught value. R naught value. So again, let's copy the circuit, and where I needed to find the R naught value. Forget about this, all these things. Gm V in would also be gone. This would also be gone. From where did I need to find the R out value? From here. I needed to find the R out value from here. Right? So this V in is gone. This V in is gone. So this will be shorted. Since this is shorted, so this will be equivalent resistance of something. 200 parallel with 100 kilo ohm. Whatever it is, I don't need that value. Why don't I need that value? Because that will be replaced by a single resistance here. Single resistance R. Let's just say that resistance is R. Or let's just write 200k parallel with 100k. And from there, 0 ampere current will be flowing. From here, 0 ampere current would be flowing. So this node will be at 0 potential only. Since 0 ampere current is there, so this 0 would be reaching here. 0 ampere current, there is no drop across the resistor. So this node will be grounded. So now this complete node will be grounded. This node is grounded like this. Well and good. Now VGS is gone. VGS is gone. Here VGS is gone. So what this will be replaced with? This will simply be replaced with a single R naught. This will simply be replaced with a single R naught. Yeah, what is the value of R naught? The value of R naught would be 1 upon lambda ID. If you remember it, 1 upon lambda. Lambda value was given 0.05. What was the ID value given? ID value we could get to know from the DC analysis. ID value was 200 micro. 200 micro. What this value would be? 1 by 5 into 10 to the power minus 2 into 10 to the power minus 4. 10 to the power 6. 100 kilo. So R naught value is 100 kilo. 100 kilo ohm. This is the R naught value we have, but we need to find the output resistance. You just need to tell this resistance looking downward. So what is the resistance value? You are going from, the gate is grounded, you are going from drain to source. You are going from drain to source. If you are going backward, you need only one step. What is that R naught? Gm into R naught of this, Gm into R naught of this, into R naught plus R naught plus this R naught, right? Because we are having R naught here as well between these two nodes. So Gm into R naught into this R naught plus this R naught plus this R naught. So this is how we find it, right? I hope you remember it. So this is the final answer. Gm R naught square plus 2 R naught. Let's just put the value. Gm value we got was 200 micro into R naught square would be 10 to the power 10, right? 10 to the power 5 it would be 10 to the power 10 plus 2 into 10 to the power 5. So if you solve it, what do you get? 2 into 10 to the power minus 4 into, so 2 mega plus 0.2 mega, so 2.2 mega ohm. So R naught value you are getting is 2.2 mega ohms. So this is the R naught value you have. So that's it about the first question of our fusion special assignment. Well and good. So just started, we saw the circuit. It was a big circuit, but we are not afraid of big circuits because we have studied the concept very deeply. You have to find the small signal voltage gain. For finding a small signal voltage gain, it is certain that I would have to do the DC analysis. From there I could get the value of Gm. Then I had the value of Gm. From there I could get the value of V naught. The special thing to note in the V naught was not just the potential with respect to ground. V naught was the potential between two nodes. So V naught was the potential Vx minus Vy. So we could find the value of Vx by simply by the current, seeing the current was 2 by 3 Gm V in. So from there I could find the value of Vx, then I could find the value of Vy as well. So how would you find the value of Vy? So for Vy you could just see the simple circuit. So it would be just the current would be in the opposite direction. From there you could get the gain, that was minus 2 by 3 V in. So from there you could write the potential of V naught by V in, and then for finding the R naught, it was a very simple circuit. From there we could find the value of R naught, and for the common gate amplifier, what is the output resistance? If you are going from drain to source, that means you need only one step. So Gm R naught 1 R naught 2 plus R naught 1 plus R naught 2. So based on that we could find the value of R naught, and small R naught value you could find from 1 upon lambda ID. Small R naught value would have been 100 kilo ohm. Well and good. Let's move towards the second question. So this seems like a very easy question. You have to determine the current I1. Your mu n x W by L Vt value is given. So you need to find the current I1. So let's just copy the circuit and find the current I1. It will it will take some time in calculations only. So you need to find the current I1. So for that you need the current here. And if you need the current here, what will be the current in Im naught? The current in Im naught would be mu n cox W by 12 Vgs minus Vt whole square, right? you have the value of mu n square x w by L, you have the value of Vt, but you don't have the value of Vgs. Let's just assume Vgs value is V, because this node is grounded, so Vgs value is V. Now the same V will be going here as well. And since there is 0 ampere current going here, then what you can write? That 5 minus V by 10k, this current, 5 minus V by 10k would be equals to the current in M naught, right? The same current will be flowing. 5 minus V by 10k would be equals to this current, mu n Cx W by L value, 100 micro by 2. 100 micro by 2. Vgs value is V minus Vt value is 1. 10 to the power 4, 10 to the power 4. So 5 minus V equals to, this would be 10 to the power 4, this would be 10 to the power 4. V minus 1 whole square by 2. That would be 10 minus 2V equals to V square plus 1 minus 2V. So V value you are getting is 3 volt. So this potential we are getting is 3 volt. Right? So if this potential is 3 volt, then what is the I M naught current? Then the I M naught current would be, just put 3 volt here. So 5 minus 3 by 10k. That would be 2 by 10k. 2 into 10 to the power minus 4, or you can write 200 microampere. So I M naught current is 200 microampere. And since they are in current mirror, so the same current would be I1. So value of I1 you are getting is, by all this analysis, value of I1 you are getting is 200 microampere. Any doubt about this question? I1 is 200 microampere. This is the answer. So if I see this question, I could know one thing, that I need the value of I1. If I need the value of I1, since they are in current mirror, so what do I need? I need the potential here, because if I need the potential here, I could determine the current in M naught. So I need the current in M naught. For determining the current in M naught, I need this potential. And if I have this potential, then I could get the value of current in M naught, and that would be the same as current in M naught, or let's just call this one as M1. This one as M1, you can call this one as M1. So that would be the same current in M1 as well, right? So for finding the current in M naught, I need the potential of V. And how could I determine the potential V? By the current 5 minus V by 10k would be equals to this current equation. From there I could get the value of V, and after putting the value of V there, I could determine the current in M naught. That current was coming out to be 200 microampere, and the same current was copied. So I1 was 200 microampere. Well and good. Now what is the next question? The next question says that your VDD increases to 5.5 volt. What will be the, determine the increase in I1. Determine the increase in I1. So this is what you need to determine. Also one more thing, here you cannot directly consider them to be in current mirror, right? You cannot directly consider them to be in current mirror. When you get the value of V, you need to determine if your M1 is working in saturation or not. M1. So for M1, what was the VDS value? That was 5. And what was the VGS value coming? VGS was coming to be 3, right? 5 volt, 3 volt. So V overdrive would be 2. So this is in saturation. So this you needed to determine. Otherwise you cannot apply the current mirror rule, right? The current would be copied only if both of them are working in saturation region. So yeah, both of them are working in saturation region. Now your voltage is increased to 5.5 volt. What will be the change in I1? This seems like a very easy question. I know everyone can solve it. This is the B part of it. Everyone can solve it, that your voltage is increased to 5.5 volt now. This voltage is increased to 5.5 volt. 5.5 volt. So let's see the method 1. This is the method 1 from which we are solving. So this is the method 1. Now it is increased to 5.5 volt. Again determine the I1 current, new I1 current. I1 new. I1 new. I1 new. So let's determine the I1 new current. For that, again we can apply the equation that 5 minus V by 10k, 5.5 minus V by 10k would be equals to mu n Cx W by L. That would be 100 micro by 2 into VGS minus VT VGS is V, VGS is V minus VGS minus VT whole square. So it would be 11 minus 2V, V square plus 1 minus 2V. So V square is equals to 10. This is what I am getting. So V value you will get is under root 10. That would be nearly 3.14. Under root 10 is 3.14 only, right? 3.16. So V value you are getting is 3.16 volt. So V is 3.16 volt. So what will be the I am not current new I can write? That would be equals to I1 new, and so that would be equals to 5.5 minus 3.16 divided by 10k minus 5.5 divided by 10k. Basically, what was the current you are getting at 200 micro. Now you are getting 233 microampere. So your I1 new is 233 microampere. So what is the change? What is the delta I? That would be 233 microampere minus 200 microampere. 33 microampere. This is your answer. Well and good. This is your answer. You can calculate it in this manner as well. This is your answer. Let's see the method 2. Let's see the method 2. What they are saying, the voltage is going from 5 to 5.5, right? So there is a very small change in the voltage. There is a very small change in the voltage, and based on that there is a change in I. Voltage is going from 5 to 5.5, so there is a very small change in voltage, and because of that there will be a change in current delta I. So can I apply the small signal analysis here? Yes, I can apply the small signal analysis. Here whatever the source is there, I will consider that as a small signal source. I will consider that as small signal source. Why so? Because there is a very small change in 5 volt potential. So I can consider that as delta V. Say yes or no. And then what this will be replaced with? This will simply be replaced with 1 by Gm. Are you getting this point or not? What I mean to say, let's see it. Arey yaar. So this was your circuit. Here your V was going from 5 to 5.5 volt. So there is a change, delta V change, and because of that there will be some change in the current, that would be delta I. So how I can make this circuit? So this is your delta V. This resistance was change is delta V. That is a small signal because the change is 0.5 volt. That you can consider as small signal. The change is delta V. This is 10 kilo. Now this much of this much of circuit can be replaced with 1 by Gm. So from here to ground, what do you see 1 by Gm? Although from here you see infinite resistance, but since you put V potential here, the current here would be GMV. So from here to ground you could see 1 by Gm resistance. From node V to ground you could see 1 by Gm resistance. So this is 1 by Gm. And what is the value of 1 by Gm? So Gm value you need to determine. Gm value. Do you know the value of 1 by Gm? Yeah. So Gm value would be root 2 mu n cux w by L id. So what is the Gm value I will take with respect to what? 200 microampere. The current I will put is 200 microampere, because what we are doing is that we are just simply making this complete circuit look like this. That this 5 volt, instead of this 5 volt you are having 5 plus V in. Instead of this 5 volt you are having 5 plus small signal V in. You are having here 5 plus small signal V in. Right? So this small signal V in is equals to delta V. This small signal V in is equals to delta V. Say yes or no. Right? So if we are doing the AC analysis, this DC bias is gone. DC bias was 5 volt. So DC bias is gone, and then we are doing the AC analysis. For doing the AC analysis, this will be replaced with 1 by GM, and this node will be going to the MOSFET. That is the other thing. But now 1 by GM will be taken with respect to this 5 volt, because our DC potential is 5 volt. So 1 by GM value will be taken with respect to that 5 volt. Did you understand this point or not? This is the method that I am going to tell you. If you are not able to understand by this method, you can go with this one as well. But that will give you a very intuitive approach of looking at the circuit. What is that thing? 5 volt is applied, 5 volt is applied. Now it is changed to 5.5 volt. That means there is a small signal change. So I can replace that 5.5 by 5 plus delta V, right? That 5.5 can be replaced with 5 plus delta V, where 5 is the DC bias and delta V is a small signal. 5 is a DC bias and delta V is a small signal, right? So delta V is a small signal. So now with respect to 5 volt, you can do the DC analysis and get the value of GM. So with respect to 5 volt, I am doing the DC analysis and I need the value of GM. So for GM, I need the value of mu n CXW by L, that was given 100 micro. Also, I need the value of ID, that was with respect to 5 volt. So value of ID would be 200 micro, that is given. So GM value you get is 200 micro Siemens. So this is the GM value, and 1 by GM value would have been 5 kilo ohm. So this is the 1 by GM value, and this is fed to this MOS, and here there is delta V applied. Here also there is delta V applied, but that's not that doesn't even matter, right? So here what will be the voltage coming? Let's call this node as small Vx. So small Vx would be 5k divided by 5k plus 10k into delta V. So that would be delta V by 3. So this node is delta V by 3. So what will be the current here? That current is delta I. So what is delta I? Delta I is GM Vx, or you can say GM into delta V by 3. So what is the value of GM? GM is 200 micro Siemens by 3 into delta V. So change in I would be equals to 200 micro by 3 delta V. So this is what you are getting as the final answer. Say yes or no. The change in I would be equals to 200 micro by 3 into delta V. So whatever the change in voltage, here what is our delta V? Here what is delta V? Here delta V is 5.5 minus 5. So from 5 to 0.5 it is changed. So what will be the change in delta I? So the change in delta I would be 200 micro by 3 into 0.5. That would be 100 micro by 3. What is 100 micro by 3? 33.33 micro ampere. And this was approximately the same answer. Here you are getting 33 microampere and here you are getting 33.33 microampere. So this is approximately the same answer. Well and good. Did you understand what did I do here? Let's just say in the examination, what do they ask? They ask you this question, they ask you this particular question, and then they say that your voltage is getting changed from 5 to 5.1, 5.3, 5.4 and 5.5. Your getting is changed like this, and in the each case you need to determine the value of delta I. In the each case you need to determine the change in current. So how will you solve it? Can you solve like this? First I will solve for 5.5, then I will solve for 5.1, 5.2, 5.3. Again and again you will not be doing that, right? Again and again you will not be doing this analysis. But if you know one thing, that there will be a small change, delta V change, you can consider as a small signal. So for a particular DC device, you can find the value of GM with respect to that. If there is a small change of delta V there, if there is a small change of delta V, with respect to that small change, I can find the value of delta I. How will I do that? Considering the small signal. So I will do the small signal analysis. I get to know that the change in delta I is equals to 200 micro by 3 into delta V. So now you can put the value of delta V 0.1, 0.2, 0.3. With respect to that, you can get the value of delta I. Are you getting this point? So this is how you can solve the question in the examination smartly if they are asking you the larger calculation, right? So for supply first one 5.1 volt, what will be the delta I? delta I would be 200 micro by 3 into 0.1. So 20 by 3. What is the value of 20 by 3? 6.66 microampere. So nearly this you will be getting. For the supply 5.3 volt, let's just say, what will be your delta I? That would be 200 micro by 3 into 0.3. So 20 microampere. So in this manner you can find the value of delta I. Well and good. Let's move towards the next question. So here you need to find the DC current, then you need to find the small signal voltage gain, and you need to find the small signal R out. Okay. So try solving it on your own. After that you can watch the solution. Yeah, so let's solve this question. I just made the IDC more clear. IDC current is the current in W by L by 4 MOSFET, this MOSFET, MP MOSFET you can say. So this is the IDC current. So first you need to determine the IDC current. So you have to do the DC analysis. So let's do the DC analysis. In the DC analysis, we will find all the values. What values we are going to find? We are going to find the values of GM, GMN and GMP, because since there are two transistors, NMOS and PMOS, so for both of them we need to find the values of transconductance. Also we will find the DC current, everything we will find. Since you are doing the DC analysis, this will be shorted, sorry, open circuited. This capacitor will be open circuited. This part will be gone. Well and good. So this is just connected like this, right? Anything else can be gone. This small signal V in will be gone. That's it. This is the circuit for small signal DC analysis. Now you can see both of them are in current mirror. So this is 50 microampere, then this current will also be 50 microampere, right? This is 50 microampere, both are in current mirror. Also it is given that I also write that all the transistors are working in saturation region. So this current also will also be 50 microampere, right? Now one interesting thing you can see is that here what will be the current? 50 microampere, right? And this is working in saturation region. So what is the formula of current for this one? That is mu n cox W by L VSG my G, let's just call this potential as V, VSG minus VT whole square. This is the formula of this current, and that is equals to 50 microampere. Similarly, this is also working in saturation region. It has the same current, mu n cox W by 2L VSG 10 minus V, source potential is just 10. So VSG 10 minus V minus VT whole square. This has the same current, right? Both of them have the same current formula because both of them are working in saturation, both have the same VSG potential, so both will have the same current. So this current will also be 50 microampere. 50 microampere. And this drives the 0 ampere current, right? The gate and drives the 0 ampere current. So this current will be 50 microampere. This current would be 50 microampere. One error I did here. What was that? W by L for this one is 1 and W by L for this one is 5. So here the current is 1 micro, so here the current would be 5 times of this. So 50 micro into 5, that would be 250 microampere current. So this current would be 250 microampere, and from upward 50 microampere current is coming. So how much current will be flowing here? 200 microampere. So what is the value of IDC? IDC value will be 200 microampere. Say yes or no. Did you understand this point or not? Let's name all these transistors: M1, M2, M3, M4, M5 and M6. What did we show? 50 microampere current here, 250 microampere current here. Current mirror, no issue. The same current is flowing in the upward most, so the same current will be copied because both are having the same VSG and both are working in saturation region. So 50 microampere current is flowing that way. 250 going downwards, so in this most there would be 200 microampere current. So IDC value is 200 microampere. Say yes or no. Well and good. So this is the answer of first question. Let's answer the second question. So for answering the second question, we need to find the small signal voltage gain. So we will have to do the AC analysis. So by doing the AC analysis, we will reduce the circuit as much as we can. So let's copy, not copy, paste. What will happen to this? This will be gone, open circuited. There will be no current. So that will be open circuited. Current source will be open circuited. If the current source is open circuit, how this will be replaced with 1 by Gm, right? From here, what do you see? 1 by Gm. I can replace this much of circuit with 1 by Gm. Now, since this is replaced with 1 by Gm, this is replaced with 1 by Gm. What is the current flowing here? 0 ampere. So, what will happen to this node? Since there is 0 ampere current in the resistor, so this node will be 0 volt only. So, this will be shorted. This node will be shorted only. And since this node is shorted, so VSG is gone. Complete VGS is gone. If complete VGS is gone, so this node will be open circuited because there will be no current. And it is given that there is no lambda mentioned. In the complete equation, there is no lambda mentioned, so there is no point of R naught. So VGS is gone. Since VGS is gone, so this will be replaced with open circuited. So this much circuit we have reduced till now. Reduced this much of circuit. What will happen to this? This capacitor will be shorted. This capacitor is shorted. Right? You need to find the R naught value, but that is the next question. Right? Now tell me one thing. How much current is there? What will happen to this 10 volt? This 10 volt will be grounded, and this 10 volt will also be grounded. How much current is there? The current here is 0 ampere. Let's just call this potential as V. So what you can write? What is the current in the upward direction? Current in the upward direction would be GMV. Say yes or no. And what was the name of this transistor? This transistor was M6. So I can write the current in the upward direction would be GM6V. This node is grounded. This node I am calling it V because I don't know the potential of this point. I don't know the small signal potential of this point. I am considering it to be V. So the current in the upward direction would be GM6V. GM6V. And that would be equal to 0 ampere. That current would be equal to 0 ampere. So what is the value of V you are getting? 0 volt. Well and good. So this V is 0 volt actually. So this is grounded. The V is 0 volt. So this node V is also grounded. Since this is grounded, here also VSG is gone. If here VSG is gone, so this complete portion will also be gone. So yes or no, right? Here VSG is 0. So this complete portion will also be gone. So we are reducing our circuit to a very small circuit, and this 5 volt will also be gone because that was the AC bias. So it is our circuit is being reduced to very small circuit. How it is reduced? Here you are having V in potential. Whenever you see a big circuit, there is no issue with that because that will be reduced with very small circuit analysis, right? Because we have studied in very depth. This 10 volt will also be gone, and forget about this DC. This is your V naught, right? Now spend only 2 minutes and tell me the gain V naught by V in. Spend 2 minutes and you need to tell me the V naught by V in gain. Small signal voltage gain. This is the reduced circuit. You all know this is the reduced circuit. This is W by L is equals to 4 here. W by L is equals to 1 here, right? You know everything because you have the value of IDC, so you can determine any value. You can determine the GM of any value. Can you determine this GM4? Yeah, certainly I can determine this GM4. What that GM4 would be? Root 2 into mu p CUX W by L into ID. So that I can determine. So everything I can determine. So it's up to you. Tell me the value of small signal voltage gain. What will be the current in this MOS? What will be the current in this MOS? That would be, what was this transistor? M3. This transistor was M3. So what that current would be? That current would be GM3 V in minus V naught, right? The current in this MOS, current in M3 MOS, that would be GM3 V in minus V naught, right? Now what it will be equals to? 0. Why so? Because this is the gate terminal. The gate terminal cannot drive any current. This is the gate terminal of this M4 transistor. This transistor was M4. So gate terminal of M4 transistor cannot drive any current. This current would be 0 ampere. So that would be equated to 0. So what will be your V naught by V in. V naught would be equals to V in. So V naught by V in would be equals to 1. That is your answer. This is the final answer. Your small signal voltage gain is 1 here. Say yes or no. So this was a very straightforward question. You would be getting confused in GMP value, GMN value. Nothing is required there. No GMP, no GMN value is required. Simply the gain is becoming 1. Right? So our target was to reduce the problem. So this is how we reduce the problem. Very simple problem. By seeing this circuit, you will be thinking, oh, what I need to do. How will I solve it? Very simple. 50, 200, 250 from upward 50 microampere. So IDC is 200 microampere. Now, if you need to do the AC analysis, everything is being reduced. This node is gone. This node is gone. Everything is gone. Nothing is left there. Only this much of circuit is left. Only 2 transistors are left. So if 2 transistors are left, then you can write the current, and that current is equal to 0. So gain is 1. That's it. Now you need to find the R naught value. So we need to find the R naught value from here. So now what I will be copying? I will be copying this circuit, because this is my final small signal circuit, right? So I have copied this circuit. Forget about this as well. What this was your 5 kilo, and you need to find R naught from here. This is my question. I need to find R naught. What will happen to this V in? This V in will be gone, right? Well and good. So let's start our solution. So for finding R naught, what I can do, I will apply a voltage V naught and get I naught out of it, right? I will apply a voltage V naught and get I naught out of it. So my target is to find V naught by I naught current. My target is to find V naught by I naught. So V naught by I naught would be equals to R naught. This is my target. So this V naught is going here as well, right? And this V naught is going here as well. This is your V naught. What is the current in the upward direction? What is the current in the upward direction in this MOS? What that current would be? GM3 V naught, right? And what is that current equals to? GM3 V naught is equals to what? 0, right? So what is the value of V naught? Because there is 0 ampere current here, no? There is 0 ampere current here. So that is equals to 0. So what is the value of V naught? V naught is 0. If V naught is 0, what will be R naught? 0 by some I naught. R naught is 0 ohm. That's it. So no GM value, nothing you need to find. The question was very simple. It just looked complex. First you need to find IDC value. What did you do? You did the DC analysis. I could get the value of IDC. Then I needed to find the AC analysis. I need to find the small signal voltage gain. So for that, I could see GMV in my, this is my reduced circuit, and GMV in minus V naught is equals to 0. So V naught is equals to V in. So the gain is 1. And here the resistance is 0 ohm only. Why it is 0 ohm? Because there is GM3 V naught current is flowing, that is equals to 0. So V naught is equals to 0. So R naught is 0 ohm. So this was a very simple circuit, very simple question. So let's move on to our next question. You need to determine the small signal voltage gain. Is there any other part of this question? No. So you need to find the small signal voltage gain. This is your V naught, and where is your V in? This is your V. Well and good. So try doing it on your own, then see the solution. Yeah, so let's solve this question now. And the thing is, R value is very large. This thing I added, the R value is very large. So you have to determine the small signal voltage gain. And if you need to determine the small signal voltage gain, certainly you need to do the DC analysis, because you would be needing the GM value. And for GM value, you need the DC current. So DC current, you need to do the DC analysis. So let's just do the DC analysis first. So I will copy this circuit. The 6 volt will be gone. This will be grounded. This will also be grounded. And for DC analysis, this capacitor will be open circuited. This will be open circuited. This V in will be gone. So this is your DC equivalent circuit, right? This is your DC equivalent circuit. Now all the transistors are biased in saturation region. It is not written, but you have to consider it, because then only you can consider them as an amplifier. So all are biased in saturation region. So since this is 50 microampere current, there is 0 current coming here. 0 current coming here and 0 ampere current coming here. This is 50 microampere, then this will also be 50 microampere. So all the transistors are having 50 microampere current. All the transistors are having 50 microampere current, right? So how can you write the GMP GMN value? So what will be the value of GMP GMP? I'm writing the values for this one MP, because both of them will be having the same GM value. Why so? Because both of them are having the same current. So what that value would be? 2 into mu P COX W by L of P into ID current, that is 50 microampere. So if you put the value 2 into mu P COX 100 micro, W by L is 4, 100 micro into 4 into 50 micro, right? 200 micro Siemens. This is your GMP value. GMP value is 200 micro Siemens. What will be your GMN value? GMN value root 2 into mu n COX W by L. Mu n COX W by L. Mu n COX is 100. W by L is 1. Mu n COX is 100. No, 400. Mu n COX is 400. W by L is 1 into ID. What is your ID? ID is 50 micro. This will also be 200 micro Siemens. Both are same. GMN is equals to GMP is equals to GM. So I can write GMP is equals to GMN is equals to GM, that is equals to 200 micro Siemens. This is the GM value you are getting. If the lambda is also mentioned, lambda is also mentioned. So what will be the value of R naught P? 1 upon lambda P ID. That would be 1 upon lambda P. What will be lambda P? Why we are finding all those things? Because in the AC analysis we will be needing all those things. No, that's why we are finding. So what is your lambda P is 0.05. What is your ID? 50 micro. So 1 by 25, 25 into 10 to the power. This is 10 to the power 250. Wait a second. 1 by 5 into 10 to the power minus 2, 5 into 10 to the power minus 5, to 10 to the power 7 by 25. So it would be 4 into 10 to the power 5. 4 into 10 to the power 5. So 4 into 10 to the power 5 ohm. And the same value you will get for R naught N as well. 1 upon lambda N ID. 1 upon lambda N would be 0.05. ID value is 50 micro. And that 50 micro. And that would also be equals to 4 into 10 to the power 5. To 10 to the power 5 ohm. So everything is same only. R naught P, R naught N. Into 50 micro, right? So this is the value of R naught P and R naught N. So everything we have for now. So now I need to do the AC analysis. So for doing the AC analysis, I need the small signal voltage gain. So I will do the AC analysis. This will be gone. Since this is gone, what this will be replaced with? Looking from here, it will be replaced with, what it will be replaced with? 1 by GM parallel with R naught. 1 by GMP parallel with R naught. This complete will be gone and will be replaced with 1 by Gm parallel with R naught. But one thing is mentioned, that is this is very large. If this is very large, you can consider it to be infinity. Say yes or no. This is very large, so you can consider it to be infinity. So that I will write later on. What will happen to this capacitor? This capacitor will be shorted. And what will happen to this capacitor? This capacitor will also be shorted. Since this is very large, you can consider it to be infinity. So from V in, if you look this side, the resistance will be infinity because that is very large, right? So this is your 6 volt. 6 volt will also be grounded. 6 volt will also be grounded. So basically this is your ground. This is your ground. Then you are having this MP. Then you are having this MN. This is your V naught. From here to ground, what is connected? R naught P. And from V naught to ground, what is connected? R naught N. And this node is connected to V in only. This node is connected to V in only, right? There is certainly something wrong in this question. So let's solve this problem now. You have to determine small signal voltage gain. So if we need to determine small signal voltage gain, we would need the value of Gm. And if you need the value of Gm, you would need the DC current. And if you need the DC current, you need to do the DC analysis. So let's just do the DC analysis first. So let's copy this circuit for DC analysis purpose, and we will do the DC analysis now. So for doing the DC analysis, these caps will be gone. These caps will be gone, right? Yeah, so this will be the circuit. So here in this MP, 50 microampere current is flowing. There is 0 ampere current here, 0 ampere current here. All of those are 0 ampere current only. This 50 ampere, the same 50 microampere current would have been flowing here as well. Here again we are taking the assumption that all the transistors are working in saturation region. If they are working in saturation region, then only you can find the small signal voltage gain. So it should be mentioned in the question, or you can take the assumption that all are working in saturation region. So we are taking this assumption that all transistors are working in saturation region. So all of them are having the same current, that is 50 microampere. All the transistors are having the same 50 microampere current. Now what do I need to find? So I need to find the value of Gm. So what will be the value of Gm? So let's find the value of Gm for PMOS. So value of Gm for PMOS would be root 2 mu p Cux W by L into IT. That would be root 2 into, what is mu p Cux W by L? Mu p Cux 100 into 400 micro into ID. What is ID? ID is 50 micro. So if you solve it, what do you get? 200 micro Siemens. That is the value of GMP. What about GMN? That would be root 2 into mu n Cux W by L ID. That would be equals to root 2 into, what is mu n Cux W by L? Mu n Cux W by L is 400 micro into ID. What is ID? 50 micro. That would also be 200 micro. Right. So GMP and GMN, both values are same only. GMP is equals to GMN, and I can call it equals to GM, that is equals to 200 micro Siemens. Now I need to tell the R naught value as well. Why R naught value? Because in the AC analysis you would need the value of R naught as well. So let's write down the values of R naught. So what will be your R naught P? Better we should write it on next page only. So what will be your R naught P? R naught P would be 1 upon lambda ID. What is 1 upon lambda? Lambda value was given 1 upon lambda P ID. Lambda P value was given 0.05, right? 0.05, and ID value is 50 micro. 50 micro. 50 micro. So what that would be? 1 upon 5 into 10 to the power minus 2 into 5 into 10 to the power minus 5. So 10 to the power 7 by 25. So 100 by 25, 4 into 10 to the power 5. 400 kilo ohm. So it would be 400 kilo ohm. Similarly, that would be only RON, because lambda n value is the same for both of them. Lambda n value is same for both of them. So what is lambda n? The same. So it would also be 400 kilo ohm. Right? So R naught P is equals to R naught N is equals to 400 kilo ohm. And that should be equals to R naught. Now I need to find the small signal voltage gain. So now I will do the AC analysis. What we will do? We will do the AC analysis. So let's do it on the next page. So let's copy our circuit. For doing the AC analysis, this DC current source will be gone, and these capacitors will be shorted. These capacitors will be shorted. Right? Now from here, what can you see? The 6 volt will also be gone. So from this particular node, what do you see? 1 by Gm parallel with R naught, right? From this particular node, what do you see? 1 by Gm parallel with R naught. This can be replaced with 1 by Gm parallel with R naught. So let's just replace this with a 1 by Gm parallel with R naught. This complete circuit here can be replaced with 1 by Gm parallel with R naught, right? But they are saying that this is very large. R1 value is very large. So you can take it nearly equals to infinity. So from here, what is the resistance you will see from this side? Since R1 is very large, you will see infinite resistance. So that side can be open circuited. This side can simply be open circuited. So this side can be replaced with open circuit, right? So what will be your equivalent circuit? The 6 volt will be grounded only. Then there is this NMOS. Then here you are calculating V naught. This source node, this node is grounded, and here Vin is connected. From gate of both of them, at the gate of both NMOS and PMOS, Vin is connected. At the gate of both PMOS and NMOS, Vin is connected. This is the Vin. And between Vin and V naught, there is R2 connected. R2 connected, right? Well and good. No issue with that. And from V naught to ground, what do you see? From V naught to ground, you see R naught P here. From V naught to ground, you see R naught P here. Between source and drain, you see R naught P, and here you see R naught N. Right? That's it. This is your final circuitry. Well and good. This is the Vin, so this Vin will be going here as well. So what will be the current here in this direction? GMP Vin. And this is the Vin, and same Vin will be going here. So what is the current in this direction? GMN Vin. Can you apply nodal at V naught? Yeah, I can apply nodal at V naught. So that would be V naught upon R naught P plus V naught upon R naught N. Outward current plus GMP V in plus GMN V in would be equals to 0. Can you write this one as V naught upon R naught P parallel with R naught N? I told you how to write it. V naught upon R naught P parallel with R naught N. We are doing it in the complete network analysis. In the complete analog electronics, like GM V naught plus V naught by R naught. So what we were doing, V naught upon 1 by Gm plus V naught upon R naught. So V naught upon 1 by Gm parallel with R naught, right? So similar thing we are doing here. V naught upon R naught 1 parallel with R naught 2. R naught P parallel with R naught N, and that would be equals to minus GMP plus GMN into V in. So what will be your V naught by V in? V naught by V in would simply be minus GMP plus GMN into R naught P parallel with R naught N. So this is your V naught by V in. Now you can simply put the final values. This was just the equivalent circuit that we got. GMP and GMN 400 micro Siemens. 400 micro, because GMP was 200 micro, right? As far as I remember, GMP and GMN are 200 micro plus 200 micro, that would be 400 micro into R naught P parallel with R naught N will be 200 kilo, because R naught P parallel with R naught N 200 kilo. 200 kilo 10 to the power 3. 3 3 4 5 6 7 10 to the power 7. 80 minus 80, so the gain would be minus 80. Answer is minus 80. This is the answer. Answer is minus 80. Well and good. V naught by V in is minus 80. This is the equivalent circuit. You just solved it and you got to know your answer is minus 80. Let's move towards the next question. Here in this question, this is a very interesting one. Mu n square W by L, Vt value, all these things are given. You need to determine the value of V in for which M1 enters into triode region. For which M1 enters into triode region, and you need to determine the value of V in for which M naught dash enters into triode region. So first we will consider that all of them are working in saturation region. First we have to consider in which region they are working. This time it is not given in which region they are working, so we will consider that they are working in saturation region. Then we will find the value of each node, potential of each node. We will find the potential of each node, and based on that we will decide what we will do, what will be the value of V in for which it will change its region. So let's do the DC analysis, and considering what we are considering all the transistors, like M naught is certainly working in saturation region because gate and drain are shorted. M naught is certainly working in saturation region. Considering M1 and M naught dash are working in saturation region. What we are considering M1 and M naught dash are working in saturation region. Based on the given bias. Based on the given bias, they are considering they are working in saturation region. This is what we are considering. So let's do the DC analysis now. What we are going to do, let's do the DC analysis and let's find if our assumption is correct or not. What we consider that is correct or not, let's find that out. So this is our particular circuit that is given, and we need to do the DC analysis. So this will be gone, this capacitor will be gone, this will also be gone, this will also be gone, and since this is the inductor, so in the DC analysis what will happen to the inductor? Omega L. What is the impedance provided by the inductor? Omega L. DC means omega is equals to 0. So inductor will be shorted. In DC analysis, capacitors are shorted and capacitors are open circuited. In DC analysis, capacitors are open circuited and inductors are shorted. Right? So I will just write a simple note here. Inductor. Look, wait. I will just write here. Inductor, capacitor. DC analysis and AC analysis. For DC analysis, this is shorted, short circuit, and this is open circuit. And for AC analysis, capacitors are short circuit and inductor will be open circuited. Just the opposite, right? Because they are inversely proportional when it comes to the frequency response, when it comes to the frequency. So for omega equals to 0, inductor will provide 0 impedance and capacitor will provide infinite impedance. For omega equals to infinity, the capacitor will provide 0 impedance and inductor will provide for omega goes to infinity, capacitor will provide 0 impedance and inductor will provide infinite impedance. So here this will be shorted, inductor will be shorted. Well and good. Now what will be the potential here? This potential will be 9.5. So here the potential will be 9.5. This potential will be 9.5 volt. The same potential will be applied here, 9.5 volt. Now we are considering all of them are working in saturation region. So this 200 microampere current will be flowing from M node dash as well, because of the current mirror. 200 microampere current here, 200 microampere current here. So current in M node dash and M1 is 200 microampere. Current in M node dash is equals to M1, that is 200 microampere. So 200 microampere current would be equals to what? Mu n Cux W by L by 2, because these values are given, mu n Cux W by L by 2. VGS value we don't know, minus VT value is 1. So that would be equals to VGS value you get is 2 volt. Am I correct? Or 3 volt. Sorry. VGS value you get is 3 volt. So for both M node dash and M1, for M node dash and M1, VGS is equals to 3 volt. Now let's just draw M1. Let's just draw M1. So what is the seam in M1? What is the seam in M1? The drain of M1 is connected to 16 volt. This is M1. The drain of M1 is connected to 16 volt. The source of M1 is connected to, this is the source. We don't know what it is connected to, but we know one thing, that this node is connected to 9.5 volt. For M1, this node is connected to 9.5 volt. And we know that VGS is 3 volt. VGS value is 3 volt. I know this thing, VGS is 3 volt. So what this potential will be? 6.5 volt. Say yes or no. VGS is 3 volt. So this potential will be 6.5 volt. And what about M naught dash? What about M naught dash? What about M naught dash? So this potential we don't know. This potential we know, that is ground. M naught dash, this potential is ground. The drain potential we also know, because the drain of M naught dash is the same as source of M1. Source of M1 is same as the drain of M naught dash. So what is the drain of M naught dash? That would be 6.5 volt. Also we know one thing, for this one as well, VGS is 3 volt. VGS is 3 volt, so this has to be 3 volt only. In which region it is working? You can directly see in which region it is working. Here VDS is greater than V overdrive. VDS is certainly greater than V overdrive. So this is working in saturation region. This is also working in saturation region. Now both are working in saturation region. So this was your circuit. Now what you are doing? You are applying some AC signal. You will apply some AC signal. Because of that, these potential will change. These potentials will change. You apply some AC signal, these potential will change because of that. And because of that, these potential will change. So you have to determine the particular value of V in for which it enters into triode region. Currently, it is working in saturation region. So when I was teaching you the basic of small signal analysis in the first lecture of MOS amplifier, what did I tell you? Why the signal has to be small? Why input signal has to be small? Why do we say small signal? The input has to be small because we need to maintain the saturation region. Now they are asking at what value of V in the saturation region will not be maintained. At what value of V in the saturation region will not be maintained. This is what they are asking. Did you understand the question? First we go to know the DC value, we go to know it is working in saturation region. Now you are applying some V in, and at what value of V in the transistor will lose its saturation region. They will enter into triode region. At what value of V in? So this is the particular question that they are asking. So now we have to do the AC analysis. Well and good. Everything is crystal clear. So these kind of questions are certainly coming in your GATE examination in near future. I am pretty sure, because these kind of concepts are left. They have asked everything. They have even asked 5T OTA. So everything can be in the next line. So yeah, these kind of questions are certainly coming. So I hope you are understanding what I want to deliver here. So what will happen to this one? This will be shorted. This will be shorted. Now this complete Vin will be fed here, and this supply will be gone. The 16-volt supply will be gone. So is there any use of the supply? No, because this Vin is completely fed here. So there is no use of the supply, and I will remove this one as well, because I know I have fed Vin to my M1 terminal. What about this one? This current source. This current source will also be gone. What do you see from here? 1 by Gm parallel with R0. R0 is given or not? No R0 given. So 1 by Gm only you see. From here you see 1 by Gm. So this can be replaced with 1 by Gm. But even if it is replaced with 1 by Gm, is there any use of that? No. Why so? Because there is 0 ampere current, so this drop will be 0 volt only. So basically this end will be grounded. This end will be grounded. These capacitors will be shorted, and this inductor will be open circuited. This capacitor is also shorted. So very easily we can draw the small signal model if we have studied it deeply. So this is the small signal model we are having, right? So our circuit is reduced to a very simple circuitry. Now we can make it more simple. How we can make it more simple? The VGS is gone. Since VGS is gone, this M0 dash will be replaced with open circuit, right? So VGS is gone, M0 dash is replaced with open circuit. Now you can find the potential of this point, Vx, and you can find the potential of this point as well, Vy, right? You can find the potential of Vx and Vy. Well and good. Why do I need the potential of Vx and Vy? So that I can define the M0, M1 and M0 dash values. Why do I need the potential of these points? So that I could define these values, the potential of these values. That's why I need the Vx and Vy potential, right? Are you getting this point? So tell me, what will be Vx? What Vx would be? What is the value of Gm here? Okay, you don't know the value of Gm. Let's just call this as Rx and this as Ry. So what will be Vx? Can you write it down? Because this will be 1 by Gm here, so it would be Rx upon Rx plus 1 by Gm. Simply potential divider. You have studied in common drain amplifier. This is 1 by Gm, this is Rx. So Rx upon Rx plus 1 by Gm. So it would simply be Gm Rx upon 1 plus Gm Rx into Vin. And what will be Vy? Vy, this Vy. For Vy, it is simply acting as common source amplifier with degeneration. If you can't remember the formulas, you can simply derive it as well. It will not take you that much of time. Simply for Vy, forget about Vx. You just need to find V0 by Vin. You just need to find V0 by Vin. What will be your answer? Gm Ry upon 1 plus Gm Rx, right? Gm Rd upon 1 plus Gm Rs. Do you remember this formula? Gm Rd upon 1 plus Gm Rs. So this potential will be minus, don't forget the minus sign, Gm Ry upon 1 plus Gm Rx. Say yes or no? Into Vin. Just only few things we can remember, right? Common source amplifier with degeneration. We remember the formula in brain only. We have remembered it because we have solved a lot of problem, and we are going to solve a lot of problem as well. So that would be Gm Ry upon 1 plus Gm Rx, and negative sign is there. So what is the value of Gm? That I forgot to calculate here. So Gm value would be 2 Id upon Vgs minus Vt, right? This I can apply because I have the value of Vgs. So 2 into Id value was 200 micro. Upon Gm will be same for all because all are having the same current. All are having the same Vgs value as well. So Vgs minus Vt, that would be 200 microsiemens. So Gm value is 200 microsiemens. So what will be the answer? 200 micro into Rx is 45 kilo upon 1 plus 200 micro into 45 kilo. If you solve it, what do you get? This would be 10 to the power 3, 10 to the power minus 4 into this is V. So let's check it out. This would be 9, I guess, right? The lower one will be 9, 10 to the power minus 4, 10 to the power 9. And that one 9, 0.9 V. This you will get is 0.9 V. What about this? Minus GM 200 micro into RY 100 kilo upon 1 plus 200 micro into 100 kilo. 10 to the power 5, and this would be 20 into 10 to the power 5. So on the upward direction, what do you see? 2 into 10 to the power minus 4. 2 into 10 to the power minus 4 into 10 to the power 5. That would be minus 0.2. No, sorry, 20. It would be 20, right? 2 into 10 to the power 4 into 10 to the power 5. So 20. And V is certainly there. Minus 20 by 21. Rx value is different. No, Rx value is 45. Rx value is 45. Rx value is 45k. So it would be minus 2V in basically. So upper one would be 2 into 10 to the power minus 4 into 10 to the power minus into 10 to the power 5. So minus 20 divided by 10 into V. So it would be minus 2Vi. Basically, you can do the calculation on your own. This is taking a bit of time for me. So Vy is, you are getting, that is 0.9 V in, and Vx you are getting is minus 2 V in. Now let's see how does your M1 and M0 looks like. How does your M1 looks? This is your M1. M1, one node of M1 is connected to only V in. No, DC plus AC we will see now. DC plus AC. So M1 is having 9.5 plus V in. M1 is having 9.5 plus V in. This node of M1 is connected to 0.9 V in. Certainly 0.9 V in is there. That is the DC AC signal plus the AC signal, that is 16. Sorry, this is the DC signal and 0.9 V in is the AC signal. And lower end is connected to minus 2 V in. Minus 2 V in. Lower end is connected to minus 2 V in and 6.5. 6.5 minus 2 V in. 6.5 minus 2 V in. What about M0? M0. This end was grounded only. This end was grounded. There is no issue with that. What this node will be? 6.5 minus 2 V in. This was M0 dash. Sorry, M0 dash. What this point would be? There was a DC signal. DC signal was 3 volt. What was the AC signal here? 0, right? Because this was grounded. In AC analysis, this was grounded. This node was grounded. When we were doing the AC analysis, this node was grounded. So AC signal is not there. AC signal is 0. So this node is grounded. This node is grounded. So 3 plus 0. So basically you are having 3 only here. 3 volt only here. Well and good. Yeah, I did a small mistake here. I'm really sorry for that. In the solution, I wrote it the negative way. This was 0.9 V in actually. This was 0.9 V in. Vx value was 0.9 V in, and this was minus 2 V in. I'm really sorry for that mistake. So this would be 6.5 plus 0.9 V in, and this would be 16 minus 2 V in, and this would be 6.5 minus 0.9 V in. Not minus, it would be plus. Right, this would be 6.5 plus 0.9 VE. So these are the potential that M1 and M0 dash are having, both AC and DC combined. So what was the question? The question was asking you to determine the value of V in for which M1 and M0 dash enters into triode region. Right? Separately, two questions are there. Question A and question B. Let's note that there is one question only. Two questions are there, question A and question B. So what did we do? First we determined the first we considered that both are working in saturation region. And when we consider both of them working in saturation region, we could determine the value of VGS. From VGS value, we could get to know that both are working in saturation region only. Our assumption was correct. Well and good. Now, based on that, we could determine their DC potential. Whatever the node M1 and M0 dash are having, we could determine the DC potential of those nodes. So M1 was having 16, 9.5 and 6.5, and M0 dash was having 6.5, 3 and 0. And they are working in saturation region. Now there is a AC signal superimposed. Since there is a AC signal superimposed, we could do the AC analysis and we could determine the potential of each node because of the AC signal, because of the applied AC signal. So this is having V in, -2 V in and 0.9 V in. So now collectively our M1 is having drain 16 -2 V in, source at 6.5 plus 0.9 V in and gate at 9.5 plus V in. And M0 dash is having 6.5 plus 0.9 V in and gate at 3 volt because there was no AC signal. So what was the question A? For M1 to go into triode. So when will M1 go into triode? When your VDS is less than VGS minus VT, right, or equal. So this is the edge of triode. So I will write VDS equals to, or better I should write this only, forget about this. VDS is less than VGS minus VT. So you can better write it as VD equals to VG minus VT, say yes or no, because S and source will get cancelled. If you don't recall it, what did I tell you? What will be VDS? VDS would be VD minus VS minus, that would be lesser than VG minus VS minus VT. So minus VS and VS is getting cancelled. VD is less than or equals to VG minus VT. So what is the VD potential? 16 minus 2 V in. That would be less than, what is the VG potential? 9.5 plus V in minus what is VT? 1, right? So 16 minus 2 V in is less than or equals to 8.5 plus 2 V in. So here would be 7.5 should be less than or equals to 3 V in. So V in should be greater than or equals to 2.5 volt. So at V in equals to 2.5, transistor goes into saturation. Sorry, transistor go into triode. Did you understand this problem or not? We could determine the potential of M1, potential of M0 dash. Then we could see what is the typical value at which it will go into triode region. So VDS should be less than VGS minus VT. So when V in is greater than 2.5, you are increasing your V in voltage. When V in is greater than 2.5, it will go into triode region. Say yes or no. Right? Now check the same for M0 dash as well. For M0 dash. For M0 dash. This is the circuit. You can simply copy it and paste it here. This is M0 dash. So for triode region, what should happen? Your VDS should be less than VGS minus VT. So 6.5 minus 0.9 V in should be less than 2. So 0.9 V in should be less than 4.5, less than or equals to. So V in should be minus sign will be here. So V in should be less than or equals to minus 5 volt. Right? So at V in equals to minus 5 volt, transistor M0 dash goes into triode region. Right? And if you keep on decreasing the value of V in, it will be into triode region only. So minimum, so this is the maximum value of V in. the value of V in at which the transistor goes into saturation region. So less than minus 5 volt, it will be into triode region only, and greater than minus 5 volt, it will be into saturation region. Are you getting this point? So we don't need to find the common point of all those things. It's not that you need to find the common point. No. There are two separate questions. One is saying that V in should be greater than 2.5, then it will go into triode, and other one is saying that V in should be less than minus 5, then it will go into triode. So this is saying that if V in is greater than this value, it will go into triode, and this is saying that if V in is less than this value, it will go into triode. So what is the typical range? The range of V in can be in this one. So if you are applying V in from minus 5 to 2.5, your transistor will always be in saturation region. Both of the transistor, M0 dash and M1 transistor. Both M1 and M0 dash both will be in saturation region if you are applying from your V in from minus 5 to 2.5. Say yes or no. Are you getting this point or not? Right? We did the DC-AC analysis, we could find the potential of each node. Then we could know that at what is the typical value when it goes into triode region. So for that, we determine the value of V in, that is 2.5 volt. So if V in is greater than 2.5 volt, it will go into triode region. So V in should be lesser than 2.5 volt to make it into saturation region. So what is the minimum value of V in at which it goes into triode region? That is 2.5 volt. Here they did not ask minimum or maximum. They just asked the determine V in for which it enters into triode region. So saturation, and then triode. So when V in is equals to 2.5, it will enter into triode region. And in this one, V in should be less than minus 5 volt. So you are decreasing, and when your V in is minus 5, it will go into triode region. Understood? So this was the question. So this was two separate questions. There were two separate questions, A and B. And if they had asked one question only, if they had asked that what should be the range of V in for which both M0 dash and M1 are working in saturation region? What should be the range of V in for which both M0 dash and M1 are working in saturation region? So what is the range? That is minus 5 to plus 2.5. Right? Let's just say this is our line. This is minus 5. This is 2.5. Here what is happening? If M1 is in triode, here what is happening? M0 dash is in triode. We can determine the cutoff region as well. Let's determine the cutoff region as well. So if we are doing it, let's do it completely only. Let's determine the cutoff region as well. When it goes into cutoff. Because this can go into cutoff as well. So when it will go into cutoff? For cutoff, here your VGS is always greater than VT. So your VDS should be less than 0. For cutoff, VDS should be less than 0 or equals to. Because VGS is always greater than VT. There are two conditions for cutoff, that VGS should be less than VT or VDS should be less than 0. So this condition we are taking, VDS should be less than 0. So 6.5 plus 0.9 V in should be less than 0. So V in should be less than or equals to 0. So V in should be less than 0.9 V in. 0.9 V in should be less than minus 6.5. So V in should be less than 65 by 9. What is 65 by 9? 63 V in should be less than 7.28 volt. There should be certainly a negative sign which I am missing. Yeah, less than negative of 7.28 volt. Right? So let's just say this is 7.28 minus 7.28. So here your M0 dash is in triode, and here your M0 dash is in cutoff. And after minus 5, it will be in saturation, and in this range M naught dash is in saturation. Say yes or no. And let's just see the cutoff point for M1. So for cutoff, for cutoff, so for cutoff M1 will be a bit complex, so let's just solve it on next page only, because there we will need to check both of the condition. So let's check for cutoff. For cutoff point of M1, the first point we will check VDS should be less than equals to 0. So what is VDS? 9. What is VDS? 9. VDS is 16 minus 2 VI. 16 minus 2 VI minus 6.5 minus 0.9 VI should be less than or equals to 0. So 9.5 minus 2.9 VI should be less than equals to 0. So minus, yeah. So 2.9 VI should be greater than or equals to 9.5. So VI should be greater than or equals to 95 by 29. For that I need the calculator. So where is the calculator? Let me bring it. So that is Vin should be greater than 2.7, and the second thing you need to check is VGS should be less than VT. So what is VGS potential? That is 9.5 plus Vin minus 6.5 minus 0.9 Vin should be less than equals to 1. So 3 plus 0.1 Vin should be less than equals to 1, right? VGS 3 plus 0.1 Vin should be less than equals to 1. So Vin should be less than equals to minus 20 volt. So this is saying that Vin should be less than minus 20 volt. Is that so? Vin is less than minus 24 minus 20. Vin is greater than 3.27. That will be the cutoff region, and here we are getting minus 20. Is the calculation correct? The calculation is absolutely correct only. So yeah, this is the range. So if Vin is greater than 3.27, let's just say this point is 3.27. So here in this range, M1 goes into cutoff, and if it is less than minus 20, what was the point? Minus 20. It will be in M1 goes into cutoff. Here also M1 goes into cutoff. So this is the scene. Everything is crystal clear now. So this is how we need to do the analysis. Just need to find the absolute potential, and then we could see in which region it will go. So that's it about this assignment. I am thinking of adding 3 more questions. I will add 3 more questions that will help you in more concepts. So we will add 3 more questions. So yeah, I will think if I need to add it now or in the end of MOSFET amplifier. So I will think it and add it. Okay, thank you. Hi everyone. So in this lecture only we will see 3 more questions. So this is the first one. Let's solve the question one by one. So this is the first question. In this question you need to determine the value of current I. So what do you see? Both are in current mirror. So this is 100 microampere. So this will also be 100 microampere. So option A is correct. Wrong. Why is it so? Why is it wrong? Because you did not consider the value of lambda as well. Here lambda is also given, and if lambda is given, then what will be the change in current? So what is the current equation? Current equation is mu n Cux W by L for saturation region, mu n Cux W by L by 2 VGS minus VT whole square So in the previous problems, we were taking this value of a current, but now since lambda is also given, so the value of current would be the previous current into 1 plus lambda VDS. So lambda value will also be considered. So now your current will depend on lambda and VDS value, right? Because lambda is not equals to 0 here. So what will be the current in M1? Current in M1 would be mu n Cux W by 12 VGS minus VT whole square 1 plus lambda. I am writing VDS1. VDS1 means VDS of this one and then VDS of this one. Why did not I write VGS1? Because I know that both of them have the same VGS value. Gate to source, both of them have same VGS value. So that's why I did not write VGS1 here. What will be the current in M2? So we have to consider M2 to be in saturation region. Let us now consider M2 be in saturation region. We can check later on. So for the moment, let's consider M2 to be in saturation. Let M2 is in saturation. So for now, we have considered M2 to be in saturation region. So mu n Cux W by 12 VGS minus VT whole square into 1 plus lambda VDS2. If M2 is not in saturation, this equation will not be valid. So I M1 divided by I M2, what that would be proportional to? What that would be equals to? Previously it was equal to W by L ratios, but here it would be equal to W by L ratios, also 1 plus lambda VDS1 and 1 plus lambda VDS2. This and this will be cancelled. This will be cancelled. This complete will be cancelled. Now only 1 plus lambda VDS1 divided by 1 plus lambda VDS2. That's it. This is the relation between IM1 and IM2. Now we need to find the value of VDS. So can we find the value of VDS for this one? Yeah, we can find, because here VGS is equals to VDS. So M1 and M2, which one was M1, which one was M2? This was M1, this was M2. This is M1, this is M2. Sorry, I forgot to show it. So we can find the value of VDS1, right? So for M1, the current is 100 microampere. That would be equals to what? Mu n Cux W by L. What is mu n Cux W by L? It is given to be 50 micro. So it would be equals to mu n Cux W by L by 2 VGS, that we don't know, minus VT is 1 into 1 plus lambda VDS. Here VDS is equals to VGS only, so I can put VGS as well. But for now, let's consider this value, this complete value, to be equals to 0. What I am saying, since lambda is very small, 0.01, that is very small. Let lambda VDS equals to nearly equals to 0. Look, if I put lambda here in place of VDS, I put VGS and I put lambda equals to 0.01, then also I can solve it, but the equation will be very complex. So first what we will do, we will consider this to be equals to 0. Then we will find the value of VGS. Let's see what the value of VGS we get. So from here we get VGS value equals to 3 volt. You can solve it on your own. 200 by 50, it would be 4, under root 4 would be 2 and plus 1. So from here we get VGS value equals to 3 volt. And now here VGS is equals to VDS, right? Here VGS is equals to VDS and that is equals to 3 volt. So what did we consider nearly equals to 0? We considered lambda VDS, that would be 0.01 into 3, that would be 0.03. I should not write should be equals to 0, I should write should be very less than 1, because if it is very less than 1, this will be considered equals to 0 only. If it is very less than 1 plus very less than 1, 0.03. So nearly it would be 1.03 only. So it will not change our answer much, right? So nearly VGS value will be 3. Here I will certainly consider the lambda value. That's why I need it. That's why my answer will be changing. But for calculating VGS value, I consider lambda to be very small and I got the value of VGS. Are you getting this point? So for the ease of calculation, I did this thing. If you consider, what I was saying is that even if you consider the lambda value, and even if you write that value and get the final value of VGS, it would be nearly around 3 volt only. It will come nearly around 3 volt only. So for the ease of calculation, I did this thing, because my final target is not to find the VGS value, but to find the current values. Are you getting this point? So my target is to find the current value. Well and good. So this is the lambda VDS value which I got, which is very less than 1. So the assumption is, so what I will write, so I can write it in this manner. This is considerable. This thing is considerable now. So VGS value I have, that is 3 volt, and that is equal to VDS only. So now what is my ratio? IM1 divided by IM2, that is equal to 1 plus lambda VDS. VDS is 3 here. I have 3. 1 plus lambda 3 divided by 1 plus lambda VDS2. What will be your VDS2? Let's just say this current in M2 is X. So for now I am writing it as VDS2 only. So now what will be your VDS2? What will be your VDS2? So VDS2 would be equals to 5 minus 10k into X. That would be equals to VD. Are you getting this point? What will be VD? 5 minus 10k into X. So VD would be 5 minus 10k into X minus 0. Source is at 0 only. So I can briefly write it in this manner. 5 minus 10 to the power 4 into X. That would be VDS2. IM1 value you know already. What is IM1 value? IM1 value is 100 microampere. Now what will be our ratio? 100 microampere, where I have considered IM2 to be equals to X. Let IM2 equals to X. So 100 microampere divided by IM2, that is equals to X. IM2 that is equals to X. That will be equals to 1 plus 3 lambda divided by 1 plus lambda 5 minus 10 to the power 4x. Well and good. So this would be 10 to the power minus 4, and in multiply with 1 plus 5 lambda minus 5 into 10 to the power 4x, 1 plus 3 lambda into x. 3 lambda into x. Well and good. Now I can put the value of lambda as well, or I should put later on. I will put it later on. Forget about it. So 10 to the power minus 4 plus 5 into 10 to the power minus 4 lambda minus 5x 1 plus 3 lambda x. Lambda value is 0.01. Lambda value was 0.01 only. Yeah. Lambda value was 0.01. So 10 to the power minus 4. Is there anything wrong in the calculation? No, everything is going fine. 0.01. So it would make 10 to the power minus 6 minus 5x 1 plus 0.03 into x. Yeah, so there was a simple calculation error. That was this would be lambda into 10 to the power 4x. So just we need to do the calculation, that's it. I hope you are doing the calculation on your own, but not watching my solutions. So don't watch my calculation at least. Do the calculation on your own. Do the calculation on your own. Right? So if I put the 10 to the power 4 lambda minus 5, 10 to the power 4, 10 to the power minus 4, 1 plus 5 lambda 4, 10 to the power minus 4, 5 into 10 to the power minus 4 lambda x. Yeah, correct. So if I put the value of lambda now, so what that would be? 10 to the power minus 4 plus 0.05 into 10 to the power minus 4, because I am multiplying it with 0.1, and here if I go, it would be lambda x would come here, it would be 4 lambda x 0.04x, right? And it would be x here as well, x plus 3 lambda x, so this will also be x. So let's just make it fine, x plus 3 lambda x, this would be x as well. So there was plenty of error in the calculation. So 1.05 into 10 to the power minus 4, that would be equals to 1.04x. so value of x is coming out to be 1.05 into 10 to the power minus 4 divided by 1.04. so let's check the final answer. .96 microampere. You are getting is 100.96 microampere. So this is the answer. So your final answer is 100.96 microampere. So this is the correct answer, right? So that's how we solved it, because the VDS value was different. So this was the method 1 of this question. There will be method 2 as well. This was the method 1. Since the VDS value was different, so because of the VDS mismatch, we were getting different values of current. Here 100 microampere and here 100.96 microampere. Now what can be the other method? Let's just say, let's assume that completely 100 microampere current is copied here. I am assuming it. That 100 microampere current is copied here. So what will be the potential here? 4 volt, right? If I assume that there is same VDS value, I am assuming that both are having the same VDS value. If both are having the same VDS value, what will happen? The 100 microampere current would be copied, because this VDS and this VDS will also get cancelled. So both current will be same if both are having same VDS value. So if 100 microampere current here, 100 microampere current here. So if I assume that 100 microcurrent is copied, then what will be the VDS value here? That would be 4 volt. And what about this? When I found the VDS value for this one, this was found to be 3 volt. So VDS for this was 3 volt. VDS1 was 2 volt and VDS1 was 3 volt, VDS2 was 4 volt. If VDS2 is 4 volt and VDS1 is 3 volt, that means VDS2 is more. VDS2 is more, and the current is proportional to 1 plus lambda VDS2. That means current is proportional to VDS. So if VDS2 is more, certainly it will have more than 100 microampere current. What is the option which is having more than 100 microampere current? Only option B. Answer B is correct. That's it. In the examination, you will do it smartly in this manner. That's why I framed the option. There is high chances that they will frame the option like this only. One thing I know is that both are not having the same VDS, so 100 microampere current cannot be copied. Right? So there will be some changes in the current. Now, if I assume that 100 microampere current is copied only, if 100 microampere current is copied only, then what will be the VDS2 value? That would be 4 volt. Right? And what is the VDS1 value that I have to find? That I found to be 3 volt. So if it is having more VDS, that means it is having more current. So the answer would be more than 100 microampere, that's for sure. And if answer is more than 100 microampere, what will happen? This voltage will go down. If there is more current flowing, this voltage will go down. Why it will go down? Because there will be more voltage drop across the resistance, so it will go down. And it will go down near to 0. Sorry, it will go down near to 3 volt. Are you getting this point? More the current, lesser the VDS. More the current, lesser the VDS. And VDS will go down to 3 volt. So that's the way you can check it smartly as well in the examination, that there is only one option framed that says that the current would be more than 100 microampere. Let's just say if the question was, instead of this 10 kilo ohm, I would have put 20 kilo ohm here. What would be the answer? Don't solve it on your own. Just try to think and tell me the answer in the comment section. I am waiting for it in the comment section. I am waiting for the correct answer. Just pause the video and put the correct answer there in the comment section. What do you think? What will be the correct answer? If 100 microampere current is flowing here, let's just say 100 microampere current is flowing here on as well. If 100 microampere current is flowing here, what will be this voltage? 100 into 20 kilo ohm, so it would be 2 volt. So this voltage will be 3 volt. And when I find the VGS value for this or VDS value for this, it is also 3 volt. So both of the VDS value are same. That means it can drive 100 microampere current for sure. because if it is driving the same current as that, then only your VDS value are same. So certainly current will be 100 microampere only. And if there was 10 kilo ohm, then what was the scene? VDS was more. If VDS is more, it will drive more current. So that's why the current was more than 100 microampere. And if VDS was, if this resistance 10 kilo ohm was 25 kilo ohm, then what would happen? Let's just say the same current is copied. If same current is copied, then how much this voltage will be? 2.5 volt. And here VDS is less. Here VDS is less, that means current is less. So current would be somewhat lesser than 100 microampere. So current would be somewhat lesser than 100 microampere. So I will write down this point very quickly. That is, let's call this as RD. If RD is equal to 20 kilo ohm, the current in M2 would have been 100 microampere. Why so? Perfectly matched VDS. If RD was, let's just say 10 kilo ohm, then current in M2 would be, if it was 10 kilo ohm, more than 100 microampere. Why so? Because VDS2 is greater than VDS1. And if RD was 25 kilo ohm, then current in M2 would have been lesser than 100 microampere. Why is it so? Because VDS2 is lesser than VDS1. Is that crystal clear? Well and good. Let's move towards the next question. So there is a black box given, or yellow box given, that has three terminal, that is a three terminal element. So that has three terminals. Okay, one terminal, two terminal, and the third terminal. So there is a yellow box that has three terminal. The current equation is given, that is V in square plus 2 V in plus 1 plus 0.05 V naught milliampere square. You have to find the small signal voltage gain approximately, and options are framed as well. So approximate small signal voltage gain you need to find. So for when we were studying amplifier, when we started with MOS amplifier, what was the scene? Can you relate this blue box with a MOS amplifier only, or MOSFET only? Input is applied, you are having the output, and there is a current. What is the current relation in that? For MOSFET, for MOS, what was the current relation? That was some Kn VGS minus VT into 1 plus lambda VDS. For given question, for given problem, what is the current? Current is some constant. Forget about some constant, it's not some constant. The current is V in square plus 2 V in plus 1. This is capital V in square plus 2 V in, because whatever the voltage that is applied, based on that the current will be written. Whatever the voltage that is applied here, forget about capital or small, whatever the voltage that is applied here, based on that this current equation is written into 1 plus 0.05 V naught. In the similar manner, we can find GM and R naught value for the given device. For the given device, we can find the GM and R naught value. What will be the value of GM? That would be delta ID upon delta VGS. Delta ID upon delta V in. This was not ID, this was simply I. Delta I upon delta V in. So GM value would be 2 V in plus 2. V value should I be written capital. 2 V in plus 2. But here we are making an assumption, that is assuming 1 plus 0.05 V naught is very lesser than 1. This is the assumption that we have made, that 1 plus 0.5 V naught is very lesser than 1. When we were studying MOSFET amplifier, what was the GM value we wrote? 2k into VGS minus VT, right? 2 into mu n CXW by L. This is what we wrote. Did we consider lambda VDS there? No. There also we ignored this factor. Are you getting this point? Otherwise, this should have come common and then we should have differentiated it. But this was not the case. There also we ignored the lambda value, right? While finding the GM for a better calculation. So the similar thing we are doing here. We are assuming that 1 plus 0.05 V naught is very lesser than 1. And later on we can check. Later on we can check if the assumption is correct or not. We will check it. The assumption is suitable or not. Whether we should make this assumption or not. So GM value is 2 Vn plus 2. And since there are options given in this question, what are the options? There is huge gap in the options, right? So whatever the assumption that you are making should be considerable. Why is it so? Because in the option there is huge gap. If this is a numerical answer type question, then you need to think. But in the option you can see there is huge gap. So whatever the assumption that you are making, that should be considerable, right? So GM value is 2 Vn plus 2. What is the supply given? That is 1 volt. So based on that, we can find the GM value at that particular supply. And this is what we do when we study MOSFET amplifier as well, right? We write GM value equation equals to 2 mu n CoxW by L ID. This is the max we have used. And then we put the DC current. Similarly, for this we found GM equals to 2 Vn plus 2. So we will put the DC GM value only. So GM value at Vn equals to 2. So that would be at Vn equals to 1. At Vn Q equals to 1 volt. So that would be 4 millisiemens. So this is the GM value you are having. Similarly, you can calculate the R out value as well. What will be the R naught value? For R naught value, this will come as it is, because what is R naught? R naught is 1 upon del I upon del V naught. What is R naught? From the output impedance, del I upon del V naught. So 1 upon del I upon del V naught. So this will be as it is, Vn square plus 2 Vn plus 1, and then differentiation with respect to V naught. So this will give you 0.05. This is already milli here. So that's why I wrote 4 millisiemens. This is already milli here. And already milli here, so I can write 10 to the power 3 upward, because this was milli, so that would go upward. So now R naught value also you will find at the DC point only. So R naught value at V in Q equals to 1 volt. That would be equals to 1 upon, we put 1, 4 into 5, 0.2, 0.2, 5 kilo ohm. Am I getting that? Yeah, so on the calculation I am getting 5 kilo ohm only. So R naught value I can directly write, it would be 5 kilo ohm. Or I should write in this manner only. V in Q would be 111. So 4 into 0.05, and here 10 to the power 3 is already there. So 5 kilo ohm. So R naught value is 5 kilo. So basically, what is your device? What is your device? So simply your device is some GM V in current is flowing. Some GM V in current is flowing. What is the direction of current? Downward. That's why I made this current downward. Some GM small signal current V in. Some small signal GM V in current is flowing. Then there is a R naught, that is 5 kilo ohm. And where you are collecting the output? Here only you are collecting the output, but since you are doing the AC analysis, you can short circuit the DC. So from V naught to ground you are having 2.5 kilo ohm as well. Not 2.5, that was 0.5 as far as I remember. 0.25. 0.25 kilo ohm. So what will be your voltage gain? Voltage gain would be minus GM into 5 kilo ohm parallel with 2.5 kilo ohm. So GM value you were getting was 4 milli into 5 into 0.25 divided by 5.25, 0.25 238 kilo into 4 minus 0.95 volt per volt. Oh, sorry. That is equals to V naught. V naught, that is equals to into VE. So this is V naught by VE. That is equals to minus 0.95 volt per volt. So yeah. But there was an assumption. What was the assumption? That you took this value very lesser than 1. You took this value to be very lesser than 1. This was the assumption that you made. So let's check that out. What this value would be? This will be some DC value as well and some AC value as well. This V naught will have some DC component as well and some AC component as well. But the AC component will be very small because gain is minus 0.95, and let's just say small signal we are applying. Let's just say in the small signal we are applying some 20 millivolt only. So what you will be getting at the output? 19 millivolt. So that will be very small. So let's just consider only the DC output. So what will be the DC output? What will be V naught DC? What will be your V naught DC? That will be this current. What that current would be? 4 milliampere, nearly 4 milliampere current. So nearly 4 milliampere current is flowing here. Vn equals to 1 is given. Vn equals to 1 is given. I am putting 1 here. This would be 1 plus. So nearly 4 milliampere current is there. So nearly 4 milliampere current is flowing through this resistance. So this will give a voltage drop of 1. So V naught DC will nearly be equals to 4 volt. V naught DC will nearly be equals to 4 volt. And if you put 4 volt here, so 0.05 into 4. So it is coming nearly equals to 0.2, which is not a small quantity. Which is not a small quantity with respect to 1. If it was 0.02, understandable. But now it is 0.2. This is not a very small quantity with respect to your 1. So this is a considerable value. So in the reality, you are not getting minus 0.95. If you simulate the circuit, I am pretty sure you will get the gain around minus 0.8, because I tried doing it. So I was getting nearly around 0.8, minus 0.8. So, but the options I framed in a way that only one answer can be correct, that is minus 0.95. Are you getting this point? I calculated the DC value because I took an assumption. What was the assumption that I took for finding the GM value? The assumption that I took was that I am considering this as nullified, but this is not nullified. When I saw the final answer, when I see the DC value here, we know DC value here, that is coming nearly equals to 4 volt, and 0.05 into 4 is 0.2, which is not very less than 1. 1.2 and 1, there is big difference. There is a difference of 0.2, so which is not very lesser than, which is not approximately equals to 1. You can't say that 1.2 is approximately 1. You can say that 1.02 is approximately equals to 1, but 1.2 is a very large quantity. So the assumption that we made, that is not 100% correct, but the answer that we are getting, that is nearly equals to 0.5 only, minus 0.5 only. So this answer can be considered. Are you getting this point? So this was the analysis. Why we did this analysis? By considering the MOSFET. So the problem was same as the MOSFET only. If you are given any circuit, if you have just a black box, you know the current equation with respect to the input voltage and the output. You can analyze that circuit. You can analyze that particular circuit. If you are just given V in, V naught, and the current I. So if you have the relation, you can find its small signal voltage. You can find its small signal model. So for that, you just need the GM value, right? Why we need the GM value? Because I am not explaining this problem in very depth. Why so? Because we have already studied it. So here the relation was between V in and I. So I versus V in. So the relation was V in square plus 2 V in plus 1. It could be somewhat like this. It could be somewhat like this. So I found the slope at this particular point. I found the slope at this particular point. This particular point, that V in equals to 1 volt. So I can take this point equals to V in equals to 1 volt. So at this particular point, I found the slope that came out to be del I upon del V in GM. So this slope is this GM that I found, and when I multiply GM with the small signal voltage, that is GM V in. When I multiply GM with the small signal voltage, I get my small signal current. So this is my small signal current. This is my small signal current, and that current will be flowing through output resistance that was given, that was 0.25 kilo ohm, and also there is output resistance for the particular device as well. What is the output resistance of this particular device? That is 1, that we were getting is 10 to the power 3 upon V in square plus 2 V in plus 1. So it was nearly equals to 5 kilo ohm. So this GM V in current was flowing from parallel combination of 5 kilo ohm and 2.5 kilo ohm. So the gain I was getting is minus 0.95. Well and good, everything is crystal clear. So this is the final answer. I hope you are able to understand it. Let's move on to our next question, and that is a very, very good question. So mu n Cx value is given, Vt value is given, V in value is also given. Now in the given question it is said that Vg naught is such that it maximizes the Vp value that can be applied while keeping all the transistor in saturation region, in maximum in saturation region, in saturation region. So you have to apply Vg naught and V in Vp value. Vg naught plus V in, and V in is Vp sin omega, cos omega t. So you have to apply Vg naught and Vp such that it is working in saturation region, or device is working in saturation region. So the option A is find the optimum value of Vg naught, and option B is find the maximum value of Vp. So let's try doing it. We will come back to this line because this line is very, very important. Till then, try to think about this line, what this line want to say. Okay, we will come back to this line. Let's just call this one as M1 and this one as M2. This will drive 0 ampere current, right? There will be 0 ampere current here. So the same 200 microampere current would be flowing here. So IM1 and IM2 both are having same current. IM1 is 200 microampere current. So here you can write is that is 200 micro. That would be equals to, because both of the transistors are in saturation region. So we are considering that to be in saturation region. Are you getting this point? We will take M1 and M2 both in saturation region. Then we will see when they goes into triode. Then we will see when they goes into triode or in cutoff. So we are considering them to be in saturation region. So we have to apply Vg0 and Vp such that they remain in saturation region only. So we are considering them to be in saturation region. So we will apply the saturation region current equation. So that current equation would be IM2 is IM1. IM1 is 200 microampere. So mu p Cux is 50 micro. W by L is 4 by 2 VSG minus VT whole square. So what is the value you are getting? 54 to VSG is 3. VSG value you are getting is 3 volt. VSG for M1 you can say. VSG for M1 is 3 volt. VSG for M1 is 3 volt. So let's draw the M1. This was your M1. This is your V0 here. This is your V0. For M1, the upper node is at 6 volt. If VSG is 3, VSG, this gap is 3, so this has to be 3 volt. Understood? M1 we have drawn, right? Let's talk about IM2. For IM2 as well, we will talk here only. IM2 is 200 microampere. So 200 micro would be equals to mu p Cox W by L. W by L is 64. W by L is 64 divided by 2 VSG of M2 minus VT whole square, right? So 32, this you are getting 32. Oh, I can solve it. Then as far as I see it, because 1.5 it should be na 1 by 4 8. Yeah, VSG of M2 would be 1.5. You can solve it. It will be 1.5 volt. So let's just make VSG. Let's just make M2. What is our M2? So for M2, the upper node is connected to V node. This is the V node. Lower node is connected to the gate of this one. Lower node, drain is connected to the gate of M1. So what was the gate of M1? What was the gate of M1? Gate of M1, 3 volt. Basically, this node was 3 volt. This node was 3 volt. So this node will also be 3 volt, right? So I guess I did something wrong here. This was 3 volt. This will also be 3 volt. And this node is connected to VG node plus V in. So I am writing VG node plus V in, VG node plus V in as capital V in. This is our capital V in. VG node plus V in as capital V in. So it has both DC and AC signal. This V node also has both DC and AC signal. Both DC and AC. It also has both DC and AC. Although for this one AC signal will not be required, but tell me what is the small signal gain of this circuit? Quickly do it and tell me the small signal voltage gain of this circuit. Pause the video, tell me the small signal voltage gain of this circuit. Although it will not be required in this question. In this question, it will not be required. When I solve it further, you will get to know it is not required. But in the examination, you wouldn't know it and you will spend time in solving that. So what will be that gain? What is the current here? If you are finding small signal voltage gain, what will happen to 200 microampere? That will be gone. So what is the current here? In this loop, 0 microampere current. Now since this 200 microampere current is gone, so this 0 microampere current will be flowing from here as well, because the current has no path. The current has no other path. Are you getting this point? In this path 0 microampere current is there, so now that 0 ampere current has no other path, so it has to flow from here only. So in the MOSFET as well, in the complete loop, in the MOSFET as well, there is 0 microampere current. So what you can say, gm v naught minus v in, gm v naught minus v in is equals to 0. So v naught by v in equals to 1. So the gain is 1 here, but that is not required. The gain is 1. The small signal voltage gain is 1. Who knows, they can ask this question in the examination. So that's why I am putting it. So the small signal voltage gain is 1. So there are two MOSFETs, M1 and M0, M1 and M2. And both should be in saturation region. So we can pick the MOSFET one by one and we can find our condition. From M1, both should be in saturation region. So for saturation, VSG should be greater than or equals to VSD should be greater than or equals to VSG minus VT. 6 minus V naught should be greater than or equals to 2. So V naught should be less than or equals to 4. This is the V naught value, right? And here what is VSG of M2 given? VSG of M2 is V naught minus V in. VSG of M2 is V naught minus V in, that is equals to 1.5 volt, right? So V naught is equals to 1.5 plus V in. This is capital V in we are talking about, capital V in. So V naught is equals to 1.5 plus V in. You can see it, VSG of M2 is 1.5, VSG. Source to gate, V naught minus capital V in is equals to 1.5. So V naught would be 1.5 plus V in. V naught would be 1.5 capital V in. So capital V in should be less than or equals to 2.5 volt. Right? And what about M0 now? Let's pick M2. Let's pick M2 now. So for M2, VSD should be greater than or equals to VSG minus VT. VT is 1. Minus 3 should be greater than or equals to V in plus 1. V in minus V in minus 1. Minus V in minus 1. So V in should be greater than 2. Right? VSD should be greater than this. So V in plus 1 should be equal. Yeah. V in should be greater than or equals to 2. Well and good. Now what is your capital V in? Capital V in is VG naught plus small v in, and that is equals to VG naught plus Vp cos omega t, right? Vp cos omega t, Vg naught plus Vp cos omega t. Now what can be the maximum value of V? Maximum value of V, that would be V in maximum, Vg naught plus Vp, and what will be the V in minimum, Vg naught minus Vp. Now most of you will get the correct answer. I know. What you will do, Vg naught plus Vp equals to 2.5 and Vg naught minus Vp equals to 2. This is what you are going to do, right? And you will put this equals to 2.5, and from there you could calculate the value of Vg naught and Vp. But why you are doing so, most of you don't have the idea. Let's get back to the previous question. What they are saying, that Vg naught is set such that it maximizes Vp that can be applied while keeping all the transistor in saturation region. So you have to put Vg naught in a way that your Vp would be maximum. Let's just assume I put Vg naught equals to 3, okay, and Vp equals to 0.5. This is my V in I am putting is, okay, that will not work actually. Let me think of it. 0.4. 3 you cannot put. 2.1. Vg naught I am putting is 2.1. 2.2 or 2.3. Vg naught I am putting is 2.3 and Vp I am putting is 0.2. Vg naught I am putting 2.3 and Vp is 0.2 cos omega t. What is the maximum value of this one? 2.5. And what is the minimum? 2.1. Does that fall into this category? V in should be greater than 2. Yeah, greater than 2. V in should be less than or equals to 2.5. Yeah. So why your Vg naught equals to 2.3 is not valid? Why is it wrong? If you solve this particular equation, that what you are going to do, you are going to put Vg naught minus Vp equals to 2.5 to 2 and Vg naught plus Vp equals to 2.5. Why we are doing so? Because this is the maximum, this is the maximum value, Vg naught plus Vp, which should be equals to 2.5, and this is the minimum value, Vg naught minus Vp, this should be equals to 2. This should be equals to 2. So from here, Vg naught value you will be getting is 2.25 volt, and Vp value you will get is 0.25 volt. So these are your answer. These are your final answer. But I am asking you one simple question, that is why this is wrong. 2.3 plus 0.2 cos omega naught t. Why this is wrong? Because in the question it is given that you have to put Vg naught such that your Vp should be maximum. You have to put Vg naught such that your Vp should be maximum. Are you getting this point? So here your Vp value is 0.2, but there is an option that you can put more Vp. The maximum value Vp can get is 0.25. And if Vp is 0.25, your Vg naught has to be 2.25 volt. Did you understand this point or not? You understood it, right? So basically, your input voltage is this. Input voltage, right? This is your input voltage, which has some DC value, and on that DC value, one sinusoid is imposed. Sinusoid or cosinusoid they have given. Vp cos omega naught t they have given, no? Okay. Cosinusoid is imposed. You only know this range, that is 2 to 2.5 volt. So this has to be 2. This has to be 2.5. You only know this range. This range is 0.5 volt. This is what you know. But you don't know this DC potential, that is Vg naught. You don't know that potential. Vg naught can vary anywhere. What if Vg naught is somewhat here? What if your Vg naught is 2.1 volt? What if your Vg naught is 2.1 volt? Vg naught can take any value from 2 to 2.5 volt. Are you getting this point? In the question, if they had asked what should be the maximum value of Vg naught, what is the maximum value of Vg naught that you can apply, what would be your answer? I want to know what should be the maximum value of VG node you can apply. What would be the answer? You have four options. 2.49 volt, option B 2.25 volt, option C 2.43 volt, and option D 2.47 volt. What would be the answer? This would be the answer, no? If I apply VG naught equals to 2.49 plus I put VP equals to 0.1 cos omega t, what will happen? Maximum value will be 2.5, minimum value would be 2.48. It's in the range. It's in the given range, and this is the range we want. We want our input to be in the range of 2 to 2.5. Yeah, it is even given in the range. So you have the liability, you have the liberty to put VG naught equals to 2.49. But in the question, what did they say? In the question, they said that your VG naught is such that it will allow VP to go its maximum value. So that's why we have to take the middle point. 2 to 2.5, middle point 2.5. 2, 2.5, middle point is 2.25. So VP can have maximum here and maximum downward. So that was the scene. I know most of you would have got the correct answer, but did you understand the problem now? Why it was written in this manner? If they had just asked what should be the maximum value of VG naught, you would say, sir, 2.499999. 2.499999. And what can be the minimum value of VG naught? That would be 2.0000001. That can be the minimum value of V naught. 2.0000001. Then you can apply any small signal and amplify that, because that will be in our range only. So maximum or minimum possible value can differ, right? And what can be the maximum value of VP? Maximum value of VP can be 0.49999. And what can be the minimum value of VP? That can be 0.00001. That is the maximum and minimum value of VP. So VP, range of VP is 0 to 0.5, and range of VG naught is from 2 to 2.5. So I will write this thing. I will remove it off. I am going to remove everything that I wrote needlessly. So range of VG naught is, VG naught can take any value between 2 to 2.5. VG naught can take any value between 2 to 2.5. I am not putting the equal sign, because if I am putting the equal sign, that means if VG naught takes 2.5 value, then your VP would be 0 only. And what will be the VP value? VP can take any value between 0 to 0.5. 0 to 0.5. Better I should write in this manner. VP can take any value between 0 to 2.5. 0 to 2.5. If VG naught value is 2, this will be your VP value. VP will be 0.5. And if your VG naught value is 2.5, your VP value will be 0. So basically, your VG naught plus VP. No, it's not necessary that it has to be 0. And also it's not necessary that VG naught plus VP has to be 2.5. It can be anything. Right? So VG naught plus VP I cannot write. So just that it should be in the range from 2 to 2.5. Your VG naught plus VP should be in the range of 2 to 2.5. Right? VG naught should be in the range, VG naught plus VP should be in the range of 2 to 2.5. It's not that, sorry. It's not that VG naught plus VP. I'm needlessly writing more statements. So let's just not write more statements. I hope you have understood the meaning of the problem. Right? You have understood the meaning of the problem. That is that you have to set the VG naught such that VP can reach up to its maximum or minimum value. So I have the optimum value of VG naught. If I have the optimum value of VG naught, the maximum value of VP can be 2.25 at that time. So these are the answers. Right? Well and good. Okay, then let's move to our next lecture now.